for coming to our dinner tonight. We have some late stragglers who may be roaming in around some of the empty tables as the night goes on. So regrets in advance if you have folks walking past you on the way in. Tonight we wanted to make this fun, enjoy, be able to share some interesting data, have an interesting dialogue, and really have an opportunity to speak to some folks who are thought leaders in our space and have had some experience with both digital PCR as well as our newest product, the ThunderBolts Cancer Panel, in the next-gen sequencing space. We're going to do this while you're having salads. We're going to try to interrupt dinner as little as possible, and part of the goal for tonight is for you to enjoy speaking with your colleagues, enjoy speaking with some of our team at RainDance, and obviously make this very, very interactive. We have three illustrious speakers with us tonight who I'll introduce shortly as we get into this. We have another collaborator in our First Access program in the back from MD Anderson, Fraser Simmons. Fraser won't be presenting at this particular event, but Fraser presented earlier today at our workshop for those of you who were able to attend. So without further ado, what I wanted to do was give you a little bit of background on RainDance and our products if you haven't had a chance to hear about us previously, and also just share with you some very basic details, and then we'll actually march into some of the specific presentations from some of our speakers tonight. So first of all, I wanted to just give you a little bit of an overview of what we do and how we do it. So we are, as many of you may be aware, we're a company based on a digital droplet platform technology. And it's a very athletic technology. We're capable of working with nucleic acids, proteins, cells, amongst other things. And the hallmark of the technology is truly single molecule sensitivity, so ultra-sensitive detection of a variety of different genetic and other types of biomarkers from both tissue as well as fluids. One way we think about this, and today most of our products are in the areas of digital PCR, next-gen sequencing, content enrichment, is really the ability to change the paradigm for how we look at the sensitivity of different targets. And on two axes, the number of targets versus the sensitivity achievable per target. The world of sequencing has moved us along the x-axis here, increasingly large numbers of targets, obviously consummating with the whole exome and whole genome, while PCR has gone the other axis, right, in terms of higher sensitivity on fewer numbers of scalable targets. As a company, our focus has really been pushing the whole frontier and thinking about new paradigms for detection of disease and research of new types of biomarkers and targets that change the way in which we can understand and access disease. All of this is grounded in a proprietary technology around droplets that we've developed, and ultimately getting to inaccessible information at low cost and in simple ways. So the three products we have today are RainDrop for digital PCR, ThunderBolts, which actually runs on the RainDrop source system, which brings together the best of our next-gen sequencing and digital PCR capabilities, and finally the Thunderstorm system for next-gen sequencing content enrichment. So as you think about how this fits in a workflow, if you think about going from sample to content to ultimately readout, in the case of digital PCR, you go from sample extraction to the RainDrop source, which generates the droplets for digital PCR, creates single molecule PCR reactions, is thermal cycled, and then reads out on the RainDrop sense. In the case of Thunderbolts, you have standard genomic extraction from whatever your starting sample type is. You have a ThunderBolts Cancer Panel, which runs on the RainDrop source to, again, create single molecule PCR-ready droplets. However, the readout, due to the diversity and range of targets, is done on a next-gen sequencing system. Today, this is the MySeq with its 2x250 or 2x200 paired-end reads. With the Thunderstorm next-gen sequencing content enrichment system, this is really designed for high-throughput, high-volume labs who need the automation and the workflow to be able to do this in very simple ways. The Thunderstorm can also go up to 20,000 genetic targets in a single assay with single molecule PCR. So it's particularly designed for medium to high, large sized panels, with the output and readout being any of the commercially available next-gen sequencing systems. So you get a sense of the portfolio in terms of what we're operating with and what we do today. Today's discussion with our key opinion leaders will be focused primarily on the RainDrop as well as the ThunderBolts Cancer Panel that we're launching here at this conference. So with the RainDrop system, focusing in for a moment, I wanted to highlight the diversity of capabilities that the system brings. So again, as you've seen, it has two boxes, the RainDrop source, which makes droplets, and the RainDrop sense, which reads them out. We built a two-box system to accommodate a pre- and post-PCR environment. We also built it as two boxes to enable unique applications like Thunderbolt's cancer panel, which runs on just the source and not the sense. We have the consumable chips, which are made by Sony DADC, the same people who make the Blu-ray discs that I'm sure your kids love and know well. And we've proven out the RainDrop capability across a wide range of applications, from rare alleles, copy number, viral load, methylation, mRNA, RNA counting, and direct RNA counting as well as most recently the Thunderbolts cancer panel, which is read out with next-gen sequencing. We've shown a very broad range of capabilities and will continue to add to these capabilities over time. So maybe just to give you a quick review of, for those of you who may not have been at our workshop earlier today, some of the key advantages of the Thunderbolts cancer panel, which is read out on Illumina sequencing. So first is it's 230 amplicons, it covers 50 genes. Andy Brooks will cover that in a little bit more detail, the details of the panel. The hallmarks of this are really superior coverage, and you'll see that in the data that the key opinion leaders present today. Importantly, it requires 10 nanograms of starting sample, and in some cases you'll hear from our presenters today even less. And from a sample standpoint, works with tissue, with FFPE, circulating tumor DNA, so plasma, as well as CTCs as well. Very high overall uniformity for this product. And importantly, with Illumina NGS, we've incorporated our proprietary direct-seq approach, which incorporates the adapters and indexers of Illumina sequencing directly into our primers, and therefore eliminates all library prep. So you have integrated library prep. You don't need to buy a separate NeoPrep system, for example, in order to move forward with the way we do this. Additionally, that integration of the direct-seq primers raises your overall sequencing uniformity dramatically, over 90 to 95%, and gives you the ability to index much higher on your Illumina sequencers, thereby saving costs. It's a simple workflow, less than 3 hours, and results in less than a couple of days. The MySeq, its 37-hour runtime, is the longest pole in that tent. And importantly, can generate data with minor allele frequencies you'll see sub 5%. As we thought about how to launch this, we've heard from many of you, how do we get to lower cost? Because that's obviously a hallmark of how you get to bigger volumes and broaden the base. And so for this particular product, we wanted to make sure that the workflow was so simple and so straightforward that we could deliver to you a product that can do, including sequencing, for as low as $100 a sample on the HiSeq, and for about $150 a sample on your MySeqs, with no upfront setup costs. You don't need to achieve super high volumes in order to get this kind of pricing. It was truly designed out of the box to be able to help get to that level. And ultimately, the Thunderbolts runs on the benchtop system, which is the RainDrop source. For those of our customers who already have the full RainDrop system for digital PCR, all of you are already enabled to run Thunderbolts. There's no additional capital equipment that's required. And our goal in launching Thunderbolts was to enable a community of users that's already pre-populated by our digital PCR users. Quickly flipping through this, over the course of today, we've had 4 presenters here. We'll have 3 of them who will be presenting this evening. So Andy Brooks, who's Chief Operating Officer at RUCDR. Fraser Simmons, who presented earlier today at our workshop at MD Anderson and focused on breast pathology and cytopathology. Tony Godfrey will be speaking tonight as Associate Chair of Surgical Pathology at BU and focused on esophageal cancer. And Andy Rim from the University of Michigan, whose focus is pancreatic cancer. So tonight, Andy, Tony, and Andy will be our 3 presenters of this evening. They are presenting based on data from a beta panel that we had given to them as part of a first access program in Q1. This conference is the official commercial launch of our Thunderbolts cancer panel. So the data you'll see with them is quite good, but the data for our commercial launch panel is even better. And so if you look at what we have here, this is our most recent and final version of the commercial launch panel. You can see ranging from fresh frozen and FFPE from 10 nanograms up to 100 nanograms. Very high number of reads per target. Exquisite coverage and uniformity across fresh frozen and FFPE samples. And as you can see here, at 100% coverage of all the targets, even at 100 hits per target. And in the case of as you'll see in some of the data from our presenters today, they were able to see this kind of data even with a beta panel. And obviously the commercial launch panel is just that much better. So with that, I'm going to turn it over to Andy Brooks to present. I think, Andy, you appear to be done with your salad, so there you go. Good timing. I'll hand it off to you. So without further ado, Andy Brooks, thank you.
Thank you, Rupam, and thanks to RainDance for inviting me to come and present some of our data, and actually, in addition to our data, kind of present the concepts and some of the challenges that we face associated with implementing new technology. And I think this is the beginning of a really interesting story with respect to all of the challenges that we face in not just analyzing samples, but actually getting samples, making them last, and getting the most utility out of samples. So what I'm going to talk about for the next short while is, what we've done to employ the RainDance RainDrop technology for both targeted sequencing as well as digital PCR, in this respect for some of our molecular oncology work, but hope to describe some of the more broad applications that we're applying. So just by way of a brief introduction, RUCDR Infinite Biologics is a biorepository program, a full-service biorepository program that enables clinical trial management right now for 5 NIH institutes, and we enable sharing programs, not just for data, but also for tissue, for nucleic acid, and for study results that facilitate currently about $1.5 billion worth of NIH-funded research. We do this same kind of work for research advocacy groups as well as a number of private sector clients, and our goal really is to speed discovery by looking at the genetic contribution for complex diseases by sharing all of these samples and this data. We've grown over the years. We have a decent-sized staff and currently have close to 20 million samples under management. We also distribute these samples, which is an important point to point out, for people that are doing analysis in their labs, and this is where identifying and implementing technologies that use the least amount of sample really becomes critically relevant. So one of the things I want to point out from our perspective is the difference between storing your sample, what we call just biological storage, versus true biobanking. And there is a difference. Bank samples proactively acquired for future testing and analysis. And when it comes to clinical trials and in the past, samples were collected usually with one purpose in mind, to measure one analyte, and then were destroyed or really not thought of again. But now people are working very hard to repurpose, expand their IRBs, expand their goals to collect samples so that we can go back to them again and again to do different analyses for a number of different molecular compartments. So a bank sample is often sent to multiple different recipients. So in the case of a lot of our controls, we will send them to hundreds of labs for different types of analyses. So to this end, a bank sample should never be depleted. So we really do consider every sample a limiting sample. Even in the case of whole blood DNA, hundreds of micrograms at some day or at some point will become limiting. When we talk about our tissue samples, they start out being limiting. So when we think about implementing technology, we look at the 5 major functions of a program like ours, which goes from sample acquisition and logistics of actually sample transport, the processing of that sample, whether it's the fractionation of sample or the extraction of nucleic acid, the storage of that sample, the distribution to the labs doing analysis, or inline analysis. And this part is really where a lot of biorepositories are growing, in that we are getting to the point where more information is needed for each sample for those deeper analyses to be done. And when we start to think about what the importance is for these samples and the analysis that we do, there are a number of what we call the functional essentials for maximizing these biological resources. So the first is really thinking about the maximal use of primary samples. There are still undefined applications for downstream analyses. So if we look now, at Thunderbolts, a year ago, that didn't exist, right? So what are the qualifications for these kinds of assays or technologies? And this leads to, obviously, the increased use for these samples. So we work on efficient processing. We maximize extraction technologies to improve yield and quality the best we can, but at the end of the day, because of all those other 4 things that I showed you we do, sometimes there's not a lot of control. And I challenge anyone who's ever worked with anybody else's samples to say, well, you know what? We understand this sample's low quality. We don't have enough. We'll just skip that one and not run it. That's the one they really want the data from, right? So, you know, even with the most qualified efforts towards efficient processing, we still have to look at technologies that are most robust, developing appropriate storage formats so we can utilize these samples effectively without jeopardizing them just with the whole in and out of a biobank process, creating renewable resources, looking at nucleic acid amplification schemes and cell line establishments. We create cryopreserved lymphocytes from just about all blood samples that come in. We did that a long time ago so that if we ever ran out of DNA, we could make more, like the Doritos commercial, you know, just keep eating, we'll make more. And interestingly enough, in the last 2 years, we've actually developed now an approach to creating induced pluripotent stem cells from CPLs. So this insurance policy now helps us create resources that otherwise didn't exist, you know, previously. So we think about these things in advance. And then also developing the appropriate distribution guidelines. So anybody that requests a sample from a biorepository, make no mistake, is making their own little biorepository. You know, I need a little more sample in case it fails, if I want to rerun it. Even though I signed an MTA, I told my friend they can have some. You know, all of these things are really being circumvented by generating more data on these primary samples using things like Thunderbolts so that we can use those samples for deeper analyses in the future. So this brings us to the RainDance Droplet technology. This is a cartoon that basically demonstrates from a complex target the ability to put single molecules inside these little droplets. The relevant applications, once these droplets are created, really are open to your imagination because we can run reactions in those individual droplets. What I'm going to show you is data from first next-gen sequencing through Thunderbolts. We actually use the same technology, the same source technology for generating droplets for digital PCR and get a readout, which I'll show you the importance of that to us. And then certainly the ability to use the limiting or unmeasurable amounts of sample that are present. So on the digital PCR side for target validation, it's a similar approach. The sample or the complex sample, which has your target and limiting amount in the context of a lot of background, is divided up into individual droplets with a single molecule ultimately in each droplet. We then do standard PCR amplification using chemistries like TACMan to then be able to count real-time the number of hits in total, which represent a hit from each droplet. This kind of digital counting is an endpoint assay that allows us not just to validate things in our clinical lab and for our research applications, but also is being used independently for us to qualify and look at the quality of sample. And the reason that this is important is when I show you in a few slides our DNA workflow and our analysis and QC workflow, up until recently, we used technologies that really were commensurate with what people were using for discovery, i.e. just regular genotyping. So I would say out of the close to 1 million samples we distribute a year, 90% of those or greater were used for standard genotyping, whether they were individual targets, microarrays, or what have you. But now the shift is really towards analyses with a higher resolution. And people are sequencing very deep, very specifically, and we're starting to wonder whether or not our quality control metrics will support the sample quality for those analyses. And what we're always concerned about are sample collection errors, contamination. So if we look by TACMan just for QC, knowing that this is the approach people are going to use downstream, that's fine. But now we have to kind of graduate to more sensitive single molecule detection to make sure the quality of our samples are commensurate with what people are going to use them to discover. And then the last workflow slide here shows the Thunderbolts targeted enrichment. Again, I think you can see the theme here. You start with a complex sample and you end up with lots and lots of little droplets that have individual molecules. Again, the RainDrop source is used, and right out of this Thunderbolts protocol is a sequence-ready product. So again, in a program like ours, when we're dealing with thousands of samples on a daily basis, having a technology that allows us to go directly into analysis, even 2 hours saved on a protocol, adds up to an immense amount of time for implementing on a large scale. So the hotspots or the important genes that we're looking at in this panel were really well selected. There are 50 genes covered by 230 amplicons. You can see the targets up here. I'm going to show you our validation, which was on colorectal samples. We compared fresh frozen along with FFPE samples to look at the efficiency and the accuracy of the panel. So there are a few markers that I'll focus on here just in the interest of time. The important thing to point out is I really think the RainDance team did a great job in identifying what targets there are by looking at what's out there in the marketplace, right? So it's, it's not an easy thing to come up, obviously, with novel targets necessarily, but we can learn from everyone that's come before us. And I think this is a good example of what's been done there in that, the entire Ampliseq panel, as well as a lot of the content from Illumina TrueSeq has been incorporated and really fine-tuned to get us to the resolution that I'm going to be able to show you. And this is just, again, another RainDance slide that just shows the simple workflow from sample to sequence. We start out with, very limiting amount of sample. We extract the sample, and again, it's really agnostic to the type of chemistry that you're using for extraction, but I'm going to show you how we account for that. It goes into the RainDrop, runs the ThunderBolts protocol, and then goes directly into sequencing and analysis. So when we think about, on an enterprise level, how we implement technology, there are a number of considerations that we have to take into account. And there are so many new technologies. As much as we would love to play all day long with all the new toys, there's just not enough time or resources to do that. So we have to very strategically choose what we're going to evaluate. And given our experience with the RainDrop for digital PCR, Thunderbolts was a natural progression for us. So first we look at specificity. So I commented on the context selection, and certainly accuracy is critical here for the level of sensitivity that we're looking for, which is the second consideration. How can we really maximize the amount of starting material? And with that limiting amount of starting material, how good is our detection, right? So we treat every sample like it's limiting. We don't ever want to have to disqualify a sample, so what can we come to expect for detection? Applicability, does it meet our programmatic goals? Are the panels well thought out? Is there ability to customize in the future? We were able to check the box on all of these things. Flexibility is key, so we certainly want to maximize the utility of our infrastructure. So being able to generate our variant data and validate it on the same instrument is a huge advantage. And certainly in the CLIA environment, if you think about it, it's also an advantage. And actually, the opinion that we've gotten from our QA group and our CLIA lab director is it's really the assay and not the box or the underlying technology that is required for validation. So TaqMan chemistry versus sequencing is a viable validation, and the fact that we can use the same instrument makes our validation and our QA process a whole lot more straightforward. Efficiency, workflow, implementation, certainly like I said, the fewer the steps, the more robust the assay makes it very efficient for us. Scalability, does the technology meet our throughput goals? And then ultimately cost. You could put cost first or last, but it factors in quite significantly when you start to talk about sample numbers on a considerable level. And that's really what enables global implementation. I could tell you over the years there are a lot of great technologies that we validated, that we love, that quite honestly we didn't put into play because the budget just didn't support the kind of data that we get out of it. And we would do it in a heartbeat, but the technology could never achieve that level. So let me tell you about our study. The study that we did was using some colorectal tumor biopsies. These come straight from the Cancer Institute of New Jersey, which we support all of the molecular diagnostics and molecular oncology work for the state of New Jersey. There are partner and development approaches like this, more specifically the personalized medicine initiative there. We ran quad sets of samples, 4 of them. We wanted to look certainly at tumor and normal adjacent and identifying variants, but also we wanted to look at fresh frozen versus FFPE. And as I mentioned this afternoon, every day people say, well, I have some samples that are fresh, some that are frozen, some that are FFPE, so certainly we can analyze them all together, right? And then they want to know why, their gene expression data might look differently, or, why their sequencing data might be different. So this gave us an opportunity to see, what utility is there for us to look across different sample types, for this kind of analysis. We used the minimum sample input that we had experience with. We compared this to the LifeTech Ion Ampliseq hotspot version 2 cancer panel, which we run a lot of. We certainly ran the RainDance Thunderbolts cancer panel, which was the reason for the evaluation, at 10 nanograms or less, and the Ion Ampliseq cancer panel at 20 nanograms, only because that was really the comfort zone from the intensive evaluation that we've done over the last couple years now. We then used digital PCR validation for the detected variants. And down here is just a screenshot from some TCGA data in 2013. And again, I'm just going to focus on a few of the KRAS and P53 mutants, which again, because these are our blinded samples that we use for this evaluation, unlike some of the other talks that you're going to hear about, we don't have the clinical history to correlate, right? We have the bare bones, and it's nice to be able to have collections like this to do this. So just one more comment on workflow considerations, because that's important to us. On the left-hand side, you can see the Thunderbolts workflow. Truly, it's a 2-day process with about 4 hours of hands-on time, which is pretty remarkable considering all of the steps and the additional QC that we do for some of the competing technologies. And the thing to really underscore on this slide is the time to technology implementation. So from the time of inception and our execution of the MOU with RainDance and looking at this technology pre-commercial launch and agreeing to evaluate it, we literally had sequencing data in 2 days. Even though we had someone from RainDance that walked us through this for the first time, the setup was no different than what we were doing for digital PCR on the source. And I can't say that about some of the technologies that we've run. By comparison, although in all fairness, it was when Ampliseq was first getting started, it was just a little over 3 months to validation of Ampliseq for the cancer panel before we could offer it on a commercial level within our lab services group. So that's a big deal for us. So most importantly, if we look at some of the performance data, the top table is the RainDance Thunderbolts results. The bottom is the Ion Ampliseq from the hotspot version 2. We saw significantly increased reads across both. These are averages of fresh frozen tumor normal adjacent and FFPE tumor normal adjacent, which was great to see given the starting amount of material. In the beta version, which is not the commercial version, we saw 100% coverage up to 100x in all of the samples. So the averages obviously collapsed across the samples that were run, and even quite respectable data at 500x. The one thing that is striking is the uniformity, and this is really what we were looking at, knowing that our FFPE samples, will never be perfect. They're kind of beat up. Granted, some FFPE samples are better than others, but it was this, lack of variability or higher uniformity which gives us a lot of confidence moving forward compared to other targeted sequencing approaches we use. Now, the Ion Ampliseq performs very nicely and as advertised, but for us, some of the workflow differences and this difference in uniformity is something that was really intriguing to us when we started to look more closely at the Thunderbolts data. But at the end of the day, it's really about the variants that we drill down and look at. And I thought that really the coolest thing that was part of this evaluation was looking at the correlation of variation frequency, not just from the sequencing data, but what we were able to validate with digital PCR on the RainDrop. So if you look at a few of these samples, and again, you can see that Ampliseq is not a poor performing technology. Really what we're looking to do is enhance on that performance by using Thunderbolts, which we were able to validate here, and really shorten our time to workflow, and put a technology in place that will allow us to put it in an enterprise level for all samples. So if we look on just the ones that are highlighted in red, you can see that the variation frequency, although for this KRAS mutant up on top for FFPE correlates nicely, you can see a much tighter correlation in variant frequency for in the fresh frozen tissue. Now, I do have one data point on the bottom, which actually shows Ampliseq picking up a variant at a low frequency, and then actually validating that with the same DNA for digital PCR. And this was not detected in the Thunderbolts panel. So it turns out that because of the increased amount of sample that was needed to run Ampliseq, we actually had to go back to that sample, cut more slices, extract DNA, and rerun it. So what happened was we got to the point in that sample that we actually were screening effectively a different part of that tumor sample or that biopsy, which are very small. And I just underscore that because this is like a real world scenario. When we have samples that come back that people that need more, we don't know if we're going to get the same complement, especially for something that's a very low ovarian frequency. If we had taken that sample and had enough to run everything from one extraction, I don't doubt that this wouldn't have validated the way that it did. But because it was from a separate sample, it, we saw different in results. And then this is some of the P53 data. Again, along the same lines, if you look at the data highlighted in red, we saw a very tight correlation in variant frequency when compared to a digital PCR. And again, this was something that was, we didn't expect would be this good, but was a real positive outcome from the analysis. So if we look at our DNA QC analytical workflow, the top for the old there is really a manual workflow that a lot of smaller labs do. There's absolutely nothing wrong with it. What we do at the RUCDR is we automate this process through different functional and analytical quality controls, with the piece de resistance being a SNP panel that we've developed that looks at quality control for ethnicity, gender, sample performance, sample uniqueness. But it kind of ended there because we knew that people were using those samples for genotyping. But what our workflow looks like under construction not only changes some of the chemistry now as we look at these analysis, using a different chemistry for looking at blood, fresh tissue, and FFPE samples, using the same automation infrastructure, but integrating now technologies like RainDance, which will allow us as a part of the DNA workflow to generate these panel results as a part of that process. So sample collection, accessioning, QC, storage, and providing this data that allows us then to have our investigators identify samples immediately that now they're going to go and look at on a much deeper level, all the while preserving that primary sample. So we don't have 50 labs doing the same screen, but allowing them to really target the samples they want because it's our responsibility to preserve those primary samples. And again, using the same technology, being able to do target enrichment as well as digital PCR validation for those samples. So, the need for biobanking's already defined. Biobanks are growing by leaps and bounds. The power for our research, the power for the development of technologies are the people that have the samples. And we work with a number of different federal and private programs so that we can get standardization across the community. However, for technology integration, that's going to be critical for molecular profiling on an enterprise scale. And what you will see is some of this profiling is being pushed onto that repository side of the framework because that data is going to be critical in making those upfront sample assessments. So specificity and sensitivity is mission critical. That is the first cut, which we were very happy with. Analysis and validation, so the integration of both of those applications is a huge advance for us. Efficiency and cost is what makes this operationalized, right? And like I said, there are a lot of technologies that we've looked at that have been very hard to bring in on enterprise scale, but this it should really be able to enable us. So the RainDrop truly does enable, at least within the context of our program, the integration of sample QC by using digital PCR to make sure that we have performance and sample uniqueness, doing the targeted molecular profiling to create that data resource that goes with every sample, and then validating those targets all within a single platform using a various suite of RainDance technologies. So I see that everyone's been served dinner, right? So that's good timing. I just have to recognize certainly our contributors and collaborators from the Cancer Institute of New Jersey. For those of you who don't know, there's no longer a University of Medicine and Dentistry of New Jersey, which was by far too long to say anyway. It's now Rutgers Medical School, and Cancer Institute of New Jersey is now formally a part of our larger program. Bob DiPaolo is the director of CINJ. Sridhar Ganesan and Lorna Rodriguez head up the translational and personalized medicine initiatives. Jay Tishfield's the RUCDR CEO, and Mike Nwasi are two people in the lab that generated all of this data. So with that, happy to answer any questions.
Maybe at this point we'll open up the floor to some questions from the group.
have you looked at deletions or insertions, like how accurately it predicts there? Or in P53, for example, there's a lot of deletions, insertions that happen.
Yeah, so we need to look at that more closely, but we need a larger sample set to do it. And these samples, again, were chosen randomly without a lot of the information. We're now going to enter into a validation with a couple hundred samples that we have data on from the foundation panel we were running, although we're transitioning that more also to a homegrown larger panel. And that's exactly the first things that we're going to look at in P53 and a number of other targets in qualified samples. So this really was more to look at the efficiency, see what markers were identified and validated. But some of those things need to be addressed very specifically, and they'll also be validated using a deeper sequencing before we put this in play as a screening tool. Looking at the data quality, I have no reason to believe that's not going to be the case, but I don't have that data to show here.
So the data showing sensitivity and specificity as a function of variable frequency. So as we go from, say, 1% to 10% to 25%, well, how does that trade-off occur? What does the curve look like?
Yeah, again, we can only reflect on the data that we have here, and some of them were very high, and I think the lowest that we had was in the high 20s. There was one low that was the 5% that had showed up in the Ampliseq, but validated by digital PCR. But digital PCR, we've looked at that, and the correlation is very tight based on the quality of the sample, if you will. What that's going to be against Thunderbolts, we don't know yet. And again, this is going to be part of this larger evaluation. If you look at the numbers, I would find it hard to believe that they're not going to continue to be tightly correlated. What I would have expected to see would have been a much lower result on the sequencing panel when compared to digital PCR. But they were extremely tight at 3 different levels. We had in the 80s, probably in the 40s and the high 20s or so. I think that might be a little more suspect when we get down into the single digits, but we have to run more samples to be able to determine it. But I have high hopes.
So you're doing spike-in controls and maybe half samples, spiked into different frequencies?
So we haven't begun any kind of clinical validation for this. And in our CLIA lab, to put this in play, because all of these samples will be run in the CLIA component for the RUCDR, we will do that. And that's typically what we do is spike-ins. We use a variety of HAP-MAP mixtures to be able to get at those frequencies, just looking at them because you're never going to find them all naturally occurring. We haven't started that yet. I mean, this data is like a week old, and it's exciting. And these were from real clinical samples because we wanted to see what those comparisons would be just out of the box. But we will have all of that data available over the coming months as we begin to validate the panel for this intended use. And yeah, it'll predominantly be spike-ins and a variety of HAP-MAP mixtures. And the good thing about having close to 20 million samples is we've got a lot of real estate to work with. So where the HAP-MAP, where we don't have, we can fill in for a lot of those.
Did you start from 10 nanogram as they advertised?
So, in some instances, we didn't even have 10 nanograms. So in the sample that we had run out of, basically, we ran it neat in Thunderbolts, which was sub 10 nanogram. We had to do multiple extractions for some of these to get enough for Ampliseq and then be able to do the validation for those. So we ran 10 nanograms, right around 10 nanograms, some a little bit less, some a tiny bit more, but certainly not even approaching 15. And for the Ampliseq, it was 20 nanograms and up.
So 10 nanograms is like 3,000 genomes, right? Or something like that.
About that.
So when you sequence at 10,000 fold, you start sequencing the same thing several times, correct?
Yep. Well, you can. So if you look at the data that led to those averages, I don't have it up here to show, but we actually accounted for the increased number of sequences. And when you look at the efficiency for sequencing, you also have to look at the relative amplicon size, right, as a function. So that was all factored into the normalization for those calculations. And what we did is, I think all the speakers have analyzed the data in a similar way so you can see it, comparably. But you're right. We could basically, if the barcodes existed, and I think that they do, is from what I was hearing in an earlier conversation tonight, is actually run more samples, bring those reads down to still achieve similar coverage for what we have here. You know, it's a very hard direct comparison. In fact, these Ampliseq samples were run on a proton and not even on a PGM because we wanted to boost the amount of reads that we got to make it more directly comparable to the MySeq given the fewer number of samples.
Yeah, Andy, as your initiative, if I understand, is to genotype and mutational profile of the biobank itself going forward, and I imagine one day going back through 20 million samples, which sounds like a Sisyphean task. But the question is, do you think that for something of that magnitude, and it's going to continue prospectively with a lot of samples coming in every week, is it more efficient for you to have tissue-specific reagents, or to go across the board with all 50 or whatever?
Yeah, you know, that's a great question. And the way that we approached this in the past with some of our SNP panels, where it kind of served, you know, that purpose in some respect, was that, you know, 75% are locked down, and 25% we apply kind of a custom approach, if you will. So when we look at the RUID panel, which is that 96 SNP panel that we run on our biomarks, there is a certain percentage that we put in for markers that we might use for inclusion or exclusion criterias for specific trials. They might be tissue-specific, marker-specific. So I'll give you an example. We recently did a study with the Army STARS for post-traumatic stress disorder. These were blood samples. We collected 100,000 soldiers. After all of those samples were collected, we had to go back to 100,000 samples, run a few markers to decide which ones we would do deeper analysis on. That's not very efficient. It's not very cost-effective. You can try reasoning with the Army. I really hope nobody's here from the Army. I want to continue to get funding. But this is how people think, and these kinds of technologies enable some of that information to be evaluated up front. So what I envision is something that is, you know, more comprehensive, but as you alluded to, having a percentage that might be specific for the study. So the vast majority of what we're screening will apply to every sample, but there is the possibility for specific trials or tissue types to make it more unique. And again, this is just a tool that will allow investigators to focus in on the samples that meet their criteria, not waste additional sample by doing more screens, and do a better job at identifying what their study participants will be, because there are more samples than anybody can afford to run.
So are you planning to run them on MySeq?
What's that?
Are you planning to run this on MySeq just to have comparison between the...
So this was run on MySeq for this evaluation. However, we can't ignore employing some of our high-seqs to do this just based on cost. So we don't have our next seqs yet. They're coming. That would be a function of cost. I don't think there's going to be a difference in sequence quality, but that will be the numbers of samples that if we can get it up to the point to barcode enough that we get the resolution we're looking for on the high-seq, we'll certainly take the lower cost as a part of this routine screening program. However, I have no problem using the MySeq for those emergent samples that need to be run on much shorter order.
No, I was getting to the point that when you're comparing Ampliseq was run on Iron Torrent versus or Proton versus the Illumina platform.
Right. No. So in this, the Ampliseq was run on the Proton, and the and Thunderbolts was run on a MySeq. I'm sorry. I thought I might have mentioned that. We could have run it on the PGM, but again, we didn't want to cut off on the number of reads. We wanted it to be as directly comparable. So we kind of, I guess, stacked the deck a little bit in the favor of Ampliseq because we have more experience with it. But you know, the data is what it is, and you know, the uniformity was superior in Thunderbolts. Great. Thank you very much.
Excellent. Thank you very much, Andy. So I think most folks are working their way through dinner. And if I might ask Tony Godfrey from Boston University to join us here. Tony's done some very exciting work in esophageal adenocarcinoma, and in particular is going to speak both to the application of the Thunderbolts cancer panel as well as some hot-off-the-press results from digital PCR in terms of some of the specific mutation validation and follow-up.
Great, thanks, Rupam. It's a pleasure to be here. And yes, definitely hot off the press. My postdoc sent the data to me last night, and I incorporated it this morning. So as Rupam said, I'll talk to you today about some of our work on esophageal adenocarcinoma. First, I'll start with just a little background on this disease, and I apologize for the next slide while you're eating. But this is, if I have a pointer here somewhere, I can deal with a mouse maybe. This is a typical esophageal adenocarcinoma that's been resected from the patient. What you see up here is the tubular esophagus. This is the stomach down here, and this is obviously the cancer, and this is typically where these tumors occur. They occur at the gastroesophageal junction. Interestingly, if you go back a few decades, just back to the 1950s, you never saw this tumor. And starting in the 1970s, the incidence started to increase. And over the last 30 or 40 years, the incidence has actually increased over 600%. And it's the most rapidly increasing tumor, solid tumor, in the United States. Along with that is a rapidly increasing mortality. It's a very deadly tumor. Average 5-year survival is less than 15%. The strongest risk factor for development of esophageal adenocarcinoma is gastroesophageal reflux disease. Again, I apologize for talking about this while you're eating. Gastroesophageal reflux leads to metaplasia and cancer. In the normal setting, the lower esophagus is protected from the acidic contents of the stomach by the lower esophageal sphincter. And if you look down the esophagus towards the stomach, as we're doing here, in a normal individual, what you see, do I have a pointer? Which one is it? Oh, the centerpiece? No. Yeah. Sorry, technologically challenged.
Should be, I think, this one right here.
Oh, got it. Center?
Although I don't think it shows up on the screen.
Okay, all right, we'll manage. We'll manage. Okay, that's fine. So what you're looking at here in this picture is looking down towards the stomach, and you can see this epithelium here is the lighter epithelium is the esophageal epithelium, and this is actually the stomach epithelium, or what we call the gastroesophageal junction here. But in a patient who has severe and chronic gastroesophageal reflux, the lower esophageal sphincter is incompetent. That allows the gastric contents to reflux up into the esophagus. And when this happens, you get erosion and damage of the lower esophagus epithelium. And what you see here in the sort of the pink tongues that are rising up from the stomach is what we call metaplasia or Barrett's esophagus, where the squamous epithelial lining is now being replaced by a columnar epithelium. And this is the risk epithelium for development of esophageal adenocarcinoma, which you can see here. There are millions of adult Americans at risk. Estimates are that anywhere from 6 to 20% of adult Americans have gastroesophageal reflux. Estimates again are 2 to 3 million Americans with this metaplasia, Barrett's esophagus, and that imparts a 5 to 10% lifetime risk of progressing to cancer. There are many opportunities for molecular tools to help in the management of these patients. I'm going to focus today on 2 of those that my lab is working on currently. The first is, unfortunately, 50% of patients who develop esophageal adenocarcinoma are diagnosed already with metastatic disease. At this point, they have a survival expectation of less than 5% at 5 years. This is in a setting where we have a high-risk population, the patients who have Barrett's esophagus, that provides an ideal group for screening. You know, it's 2 to 3 million people, and we know who they are for the most part. So this is one area that we could address. Another area, very different, is that the patients who are diagnosed with earlier stages disease, stages 1 through 3, frequently undergo neoadjuvant therapy prior to surgery. So this would be chemotherapy or chemotherapy plus radiation, the goal being to sort of minimize the disease before surgery. Unfortunately, only 40 to 50% of the patients actually respond to therapy, and even worse, 10 to 20% of patients progress while on therapy. And for a lot of them, what that means is that while they may have been surgically treatable to start with, after 8 to 10 weeks of chemotherapy and radiation, they are no longer surgical candidates. And at that point, unfortunately, their outcomes, again, are very, very bad. So the way that my lab is approaching these two challenges is to look at circulating cell-free tumor DNA, the so-called liquid biopsy. I took this figure from a recent paper from the Hopkins group. And the theory of this, of course, is that as the tumor grows, it sheds DNA. That DNA gets into the circulation, into the plasma. And you can use this for early detection and monitoring, theoretically. You can also use it to determine the right targeted therapy. If you can identify the mutations that are present in the tumor by analyzing the circulating tumor DNA. You can monitor response to therapy, and you can actually watch the tumor mutations, the clonality of the tumor change in response to selective pressure from therapeutics. So far, there's very limited data on esophageal adenocarcinoma. This again is data from the recent Hopkins paper in 2014. They looked at a set of 21 patients with gastroesophageal cancer. So this is actually a mixed bag. This is 3 different tumor types. It's esophageal adenocarcinoma, it's stomach cancer, gastric cancer, and it's also esophageal squamous cancer, which is a very different disease. And again, only 21 patients. The good news, however, is that in the 7 patients that have metastatic disease, as shown here on the left, and you see these guys right here, 100% of them had detectable circulating tumor DNA in the plasma. The amounts were not as high as for some of the other tumor types. You can see on the graph on the right there, I've again highlighted the gastroesophageal group with the red oval. But typically, there were between 10 and 100 copies of tumor DNA per mil of plasma. When they looked at the earlier stage patients, there were only 14, but approximately 60% of the earlier stage patients had detectable circulating tumor DNA again, so that's pretty good. And again, 100% of the metastatic patients. So this is promising, and we're hopeful that we can build on this and use this. So as we come back to our 2 questions, what we hope to do to address these questions is, number 1, we need to determine the feasibility of using circulating tumor DNA as a potential cancer detection tool in patients with esophageal adenocarcinoma. And to determine the feasibility of that, we need to look at a large number of patients with various stages. In particular, we need to look at patients with early stages. So that's what we're building up to. And then when we come to looking at the neoadjuvant therapy question, we need to determine if the circulating tumor DNA quantity changes during the course of therapy. What we'll be looking for in this regard is, as a patient undergoes their first rounds of chemotherapy and radiation, does the tumor marker drop in their plasma? That's been seen for ovarian cancer and for breast cancer already. And I wouldn't be here today if we weren't using the RainDance platforms. Okay. So our group recently published a paper in Nature Genetics on whole exome sequencing of 150 esophageal adeno specimens. This was in collaboration with our colleagues at Dana-Farber. But as we move forward with this, we need a targeted sequencing platform that we can use to verify the data that we already have from the exomes, but also for analysis of new tumors, because one of the things that you need when you start moving into the plasma circulating tumor DNA realm is you need larger volumes of plasma than you're typically using. So just for example, as we prospectively collect samples now, we're collecting 2 tubes of blood from patients, giving us sort of 8 to 10 mils of plasma. And we don't have that on our retrospectively banked specimens. So we need a new tool, because exome sequencing is obviously too expensive. When we first conceived the project, we planned to use the Ampliseq technology, not necessarily the cancer hotspot panel, but certainly the Ampliseq technology and PGM sequencing. But then when we bought the RainDrop system for digital PCR, Darren Link at RainDance mentioned the Thunderbolts panel, and we thought it would be a kind of a good idea up front to test them head to head. So that's what we did. Initially, we did 8 samples with each. These are tumor samples, not plasma samples. All of the library construction was performed in-house by my postdoc, Jennifer Jackson, who has been working her tail off to present this, to get this data for me to present. And the libraries, as I said, were made in-house, but then we sent out the samples for sequencing to outside sequencing facilities. You've seen this several times already tonight, so I'm not going to harp on this. You get great coverage and you get good uniformity, even though this was the beta panel. And I just highlighted here with the red arrows, two cases. We used 4 tumors, either 100 nanograms or 10 nanograms. And the 2 10 nanogram samples, you can still see that you're up in the 92-93% uniformity at 0.2x of the mean coverage. So again, very good coverage, even with the beta panel. We also compared the minor allele frequencies with Thunderbolts versus Ampliseq, and great correlation. This is just an IGV snapshot of one of them. This is a KRAS G12V mutation, called at 46% in Ampliseq and 47% in the Thunderbolts. But and I'm not a next-gen sequencing expert, and my lab doesn't have a ton of experience with this, so I'll be interested to see what the audience thinks. But our experience with this is that the Illumina data is a lot cleaner than the PGM data, so we're quite happy with this. You can see that in the top panel here. I think you can see all of these sort of missed calls that come out of the PGM sequencer, that and the Illumina data, at least to us, looks to be a lot cleaner. The last thing we did to evaluate the Thunderbolts was to look at concordance from run to run. So this is now 2 independent library construction processes and 2 independent runs on the MiSeq. And again, you can see you get a high concordance for the minor allele frequency. So in our hands, if we compare Thunderbolts versus Ampliseq, both of them in our hands work with 10 nanograms of DNA, compared with, I think, the minimum for TrueSeq is something like 150 or maybe even more. But probably the most important thing is that Jen, my postdoc, said that the Thunderbolts workflow is really much, much, much simpler than the Ampliseq. I would echo what Andy told us earlier. We didn't take 3 months to get our first data off the Ampliseq, but it took us a good month. And we had quite a lot of problems getting it to work first time, versus Thunderbolts, which worked literally first time for us. It was very simple. There are fewer steps. Jen likes the fact that there are less washes, less chance to lose the products, as she said. And again, the fact that once you've made the library, you're ready to go straight on the sequencer, as opposed to all the quantification that you have to do and the one-touch that you have to do for the Ampliseq protocol. And again, I've already mentioned, we like the fact that the Thunderbolts is designed to give us data from the Illumina sequencers. I think that certainly based on PGM sequencing, I don't know about with proton sequencing, but certainly based on PGM sequencing, I think we're going to see a significantly lower cost per sample, and that will help us, of course, being an academic lab and dependent on NIH funding. So that's it for the Thunderbolts. The next thing that we wanted to do was to verify these mutations and to literally actually to gain experience with the digital PCR platform. So we selected 10 of the tumors that we had sequencing data on. Some of it was just exome data. And we picked 6 unique mutations in 3 genes, P53, KRAS, and SMAD4. And you can see the mutations that we selected here. For P53, it was a single mutation in 4 samples. We had 3 separate KRAS mutations, and then we had 2 different mutations at the same location in the SMAD4 gene. We don't have a lot of experience designing digital PCR assays. I don't think anyone does. So for this first set, we decided to take advantage of a service from IDT, where you can send them the sequence, and they'll design your primers and probes for you. Specifically, they use these new probes called Zen probes. I'm not sure if anyone's familiar with those. They're double quench probes. We labeled the wild type with TET, the mutant with FAM, and theoretically, at least, as you can see in the right panel here, the fact that these double quench Zen probes have 2 quenchers in there and that the internal quencher is closer to the fluorophore, it's supposed to give you lower background. And this is the spec sheets from IDT. You see the low background. These are regularly labeled probes. This is the Zen probe set. We didn't see that with our probes when we ran them. These are our, and I apologize, you probably can't see that. Can you even see that at the back? Okay. These are our wild type probes. So 3 of them looked okay, very much like the published data. This one's terrible, high background, very little signal. And these ones, low background, but still very little signal. And it was even worse when we went to the mutant probes. Only 1 of them looked good. So literally, these probes came in a couple of weeks ago. We are going back to IDT to see what they think of them. But even though they look pretty bad, the digital PCR data didn't look so bad. 5 of the 6 assays that we got from IDT actually gave acceptable data in the first run using just standard conditions that we were given from RainDance for these assays. This is one of them. This is the P53 assay. In the left panel, you're looking at no template control, so reasonably clean. A little bit of spray out on the x-axis. And the next panel in the middle, we have just the wild type P53 control. You can see the nice positive group and relatively clean. A few positive droplets in the positive gate. And on the right, we have the tumor that was 23% minor allele frequency. This is 2 more assays. Top panel is SMAD4, one of those. Again, no template control, wild type control in the middle, and the positive tumor, and then the KRAS G12V. So again, first run, no optimization, just standard conditions, doesn't look too bad. The last one I'm going to show you is the KRAS G12R mutant. And in this case, we did a quick dilution. This was one of the better looking ones. So we did a quick dilution just to see what the sensitivity might be. We have the wild type only up here, just a couple of false positives in the positive gate. And then we go from 50% down, 10, 5, 1, and maybe even as low as 0.5%. Although I would say that I would be comfortable calling 1% with this assay. And again, at this point, no major optimization attempted. So overall, first of all of the mutations in the tumors were verified, as you would expect, given the fact that we had sequencing data from at least 2 platforms on all of these. And as the other presenters have already mentioned, the allele frequencies with the digital PCR versus the sequencing platforms were highly concordant. So finally, finally, as in again yesterday, we looked at 5 plasma samples that we had, or these are actually serum samples that we had available from the cancer patients. We looked at 4 who had the P53 mutation. What you're looking at here again is the no template control. There are 3 positives in the positive gate. The wild type, in this case, unfortunately, was a little bit more noisy. We had 11 positives in the positive gate. And then on the right side in the top panel is the actual tumor sample where we had, I believe that was somewhere around 40 or 50% mutant frequency. In the bottom panel, we're looking at the 4 serum samples from the patients who had this mutation. And on the left, patient 310, we saw 14 in the positive gate. Questionable whether that's positive or not. 315 had 3. The one on the end, 1102, had 5. And then this guy here is the one that we're kind of interested in, had 19 positives. But I'd be interested to see who here would call that. I wouldn't. I wouldn't call that positive. I would say that's interesting, but the assay needs to be cleaned up a lot before we could go anywhere with that. And this, I think, really illustrates one of the problems that we're having right now with this, is that this spray on the x-axis is causing a little bit of a problem for calling very rare variants. This one's a little bit better, though. This is a KRAS G12S. Again, top left, no template control. In this case, very, very clean. The wild type, again, very clean. The tumor, as you'd expect. And in this case, we've got 8 positive droplets in the positive gate. And this one I'd be more comfortable with. I obviously want to see replicates, but for now we're saving the precious serum DNA that we have until we've cleaned up the assay some. But we're hopeful that this one will actually end up being real. Just for your information, that's a 0.04% allele frequency that we're looking at, if that's true. Up until this point, we hadn't looked at the actual patient data for these samples. We literally looked at the exome data. We identified mutations in genes that were in the hotspot panel. We selected those tumors. We then applied the Ampliseq or the Thunderbolts to them. And then from there, as you've seen, we went through and designed assays based on which assays looked best on our first runs. So when we went back and looked at the staging of these patients, we probably could have done ourselves some more favors if we had picked some later stage. All of these patients are stage 2 or less, and 3 of them are stage 1. So it's maybe not surprising that we're not seeing a whole lot of circulating tumor DNA in these first 5 cases. But I'm encouraged that we might have 1 positive, and the P53 we'll have to follow up on. So in summary, in our hands, Thunderbolt is a great tool for mutation detection with low DNA input. We intend to be using it going forward. I think that it's safe to say that digital PCR can easily verify mutations with 1% allele frequency or greater, even with minimal optimization of the assays. I think that detection of allele frequencies lower than that is going to require optimization, and specifically we're going to need to identify what the source of the background spray is and to overcome that. Having said that, I do think that detection of these lower allele frequencies will be easier if we can put more DNA in. We started, as I said, with 2 to 3 mils of serum, and we only used a fraction of that in these assays. But what we've observed so far is that the background doesn't seem to increase with the increasing amount of target. So if that holds true, then the more you put in, you should be able to see that positive cluster come out above the background in the future. And of course, what that really leads to is I think the field needs a statistical approach for calling these rare mutations. We can't be standing up here saying, oh, what do you think? Is that real or not? We have to come up with a better way of doing that. I really need to acknowledge Jennifer Jackson, my postdoc, who has quite literally, for the last 2 weeks, hardly left the lab to try and generate this data, and Anders Stahlberg, who is a visiting professor in my lab right now. The samples that we ran here were collected by my longtime colleagues, Jim Lukatic and Arjun Panathar at Pittsburgh, and our histotech out there who cuts all the samples and ships them all to us whenever we need them. And of course, I have to thank RainDance, in particular Darren and Michael, for your help, and the indispensable Corey, without whom I don't think we'd have any of the assays working yet. So that's great. Okay, thanks.
I'm curious if, and I apologize if you already mentioned this, but are you planning to run over just normal healthy donors with a serum to see what kind of background you get?
Yeah, once we have the assays set, and once we have the early stage cancer patient data, one of the nice things about our Pittsburgh colleagues cohort is that they do a lot of surgeries on patients with benign esophageal disease, and we have all of those samples banked. So, but we're waiting until we have the assays optimized before we think about that.
And is there any reason you're using serum as opposed to plasma, or is that just the sample type you have?
That's the sample type we have for these patients. These collections go back to 1999, and at the time we were doing a single red top tube collection, single spin, so they were suboptimal for the kind of work that we're trying to do. But we decided to give it a shot because the only real sort of downside to serum samples is the potential for having some leftover white blood cells in there, giving you background DNA, or that some of the white blood cells could be ruptured and release the DNA during clotting. And one of the advantages of the RainDrop system with 10 million droplets is that we can take hundreds of nanograms of DNA. So if there's more background, that's okay. What we actually saw was that we still only got about 10 to 30 nanograms per mil. So we're right in the range of what people were expecting to see from plasma. But going forward, we are definitely doing 2 tubes of EDTA and plasma preparation protocols.
So the graphic showed at the beginning about secreted was relatively low compared to some other tumor types. Yeah. Was that from late stage?
That was the metastatic patients. That was the 7 metastatic patients.
Is there anything you can say about this early stage?
The only data I'm aware of is the stuff that I just showed. Yeah, so it's on the low end, but still, as I said, it's 10 to 100 copies per mil. So it should be detectable. We should be able to see it.
Fraser, I think you had a question.
Yeah, Tony, from the cytology side of things, I mean, with fine needles or exfoliative cytology, particularly with the fine needles of deep sites or scraping the esophagus, for example, and we turn backward flips to try to make cell blocks in order to put things through formalin fixation and so we can dissect. And yet often on the direct smears, alcohol fixed, we see clusters of tumor cells that can be microdissected off. Do you think that this technology would have a potential advantage for that sort of very small focused enriched sample on an alcohol fixed smear?
An advantage over something like
trying to make cell blocks in order to view tumor cellularity and form tissues.
Yeah, I mean, obviously, if you can detect 1% or less, if you have that, then why bother to go to the hassle of enriching and trying to do those other steps? I think that would be a clear application. Not sure where you're using cytology for esophageal samples, but you're doing the cytosponge?
Yeah. No, not so much for esophageal. I was thinking, in the brushing setting, you could do that, but usually there's good enrichment. But particularly when the radiologists go to deep, para-aortic nodes and things like that.
I see. Yeah. EBUS. Yeah.
We have a high failure rate when we try to take the sample. We put it in 50 mLs of RPMI. We spin it down. The lowest paid person in the department tries to pick out the little fragments from the bottom, and then the second lowest paid member of the department takes it out and puts it into the wax the next day. And we're often disappointed.
I would suggest rather than investing $125,000 instrumentation, pay your people some more. But okay, great. Thanks.
Thank you.
Thank you, Tony. Great, thank you. So I realize that Andy Rim from the University of Michigan now stands between you and your dessert. So hopefully everyone has enjoyed the dinner so far and the lively presentation and dialogue. With that, I want to introduce Andy, who heads the pancreatic cancer program at the University of Michigan. Andy?
Thanks, Rupam. So I'd like to first thank Rupam for saving me from another dinner I had to go to with a lot less quality food and some more boring people. AACR didn't hear that, by the way. So I'd like to thank RainDance and Rupam for the invitation to present some really exciting data that we just got hot off the presses about a couple weeks ago, where we're using Thunderbolts enabled sequencing now to analyze very low amounts of DNA from pancreatic cyst fluid. So my laboratory is interested in understanding the cellular and molecular events that occur when a precancerous lesion decides to turn into a cancer, in the pancreas, that is. And it's our hope that by understanding this biology, we can then develop new assays to achieve earlier diagnosis of pancreatic cancer. 80% of patients who are diagnosed with pancreas cancer will have locally advanced or metastatic disease, and as well as to alter patient treatment. So there are two major precancerous lesions of the pancreas. The first is the pancreatic intraepithelial neoplasia, or the Panin lesion. This can lead to ductal adenocarcinoma, and they're microscopic, making them impossible to detect on CT scans, MR, or endoscopic ultrasound. So here, the challenge clinically is to detect Panin lesions that we cannot detect on any current assay. The opposite is true for the more common pancreatic precancerous lesion, which are cystic lesions, and specifically we'll talk about IPMN lesions or intraductal papillary mucinous neoplasias. Here, these lesions can devolve into cyst adenocarcinomas or ductal adenocarcinomas, but in contrast to Panin lesions, these lesions are readily detectable on CT scan or MRI. They have a fluid-filled component, which provides really nice contrast to be able to pick these up in a pancreas CT or a pancreas MR. And with the increasing utilization of CT scans or MRIs over the past 2 decades, we've seen an explosion in the diagnosis of IPMN incidentally in our patients. Seems like anytime you have a stomach ache or itch, you walk into the ER, you get a CT scan or an MRI. That's the physical exam that we use now. Be that as it may, we have an incidence now of about 1 in 1,000 Americans over the age of 60 being diagnosed with IPMN lesions. But only a small portion of these lesions will progress to cancer, and hence that is the clinical conundrum that's facing gastroenterologists, radiologists, and surgeons. Because if we can catch these IPMNs early enough, we can prevent them from actually advancing to cancer just by cutting them out, either by a distal pancreatectomy or a pancreaticoduodenectomy or a Whipple procedure. But the problem is that we kind of need our pancreases to digest the filet mignon that we just ate and to control blood sugars. So patients who undergo these surgeries, these really big surgeries, are at really high risk for developing brittle diabetes and malabsorptive disorders. So if we can catch these IPMNs early enough, we can do the surgery, save them from a cancer, but we usually introduce another disease in its place. Now, there are in place clinical criteria that dictate which patients we should send for surgery because we think that these IPMNs look nasty or worrisome. And these criteria, which are called Sendai criteria, are basically opinions of a consensus panel. And they have very little clinical evidence for their use. Be that as it may, it's based on the radiographic appearance of these cystic lesions on CT scan or MRI, as well as cytology of cyst fluid. But these criteria are deficient, and that's putting it mildly. These criteria have very poor sensitivity. Only about 10% of all IPMNs that are Sendai criteria negative or deemed clinically benign will progress to cancer. On the other side, we know that they have very poor specificity. So of all the IPMN lesions that are cut out because they are Sendai criteria positive, only 60% will have advanced pathology in the form of dysplasia or invasive carcinoma. Now, another way of saying this is that 4 out of 10 patients who are getting their pancreases cut are doing so for benign pathology. And so we're doing a lot of procedures. We're doing a lot of procedures on patients for pretty much no reason. And this rate is going to increase as we do more and more CT scans and MRI. So it's clear that we need to develop better ways to predict whether or not an IPMN lesion that we detect incidentally on CT scan or MRI will progress to cancer. And we've been inspired by work from the Kinsler and Vogelstein groups, in which they've done exome sequencing of cyst lesions taken from patients who have advanced carcinoma or benign disease. And what they're able to show is that KRAS and GNAS mutations are highly associated with advanced pathology. And so the question that we want to address in our laboratory is whether or not we can use this information to then predict which of these patients will have invasive or dysplastic pathology before the decision of surgery is made. Now, as I mentioned, these lesions are fluid-filled, and we can access this fluid quite easily using endoscopic ultrasound in a non-invasive procedure. But there are plenty of obstacles in trying to do genetic analysis of pancreatic cyst fluid. First, the sample is limited. A 1 centimeter lesion will yield about 1 milliliter of fluid. And most of this fluid is already dedicated to preordained analyses. And this is based on current clinical standards, the Sendai criteria. So every time we do an endoscopic ultrasound and we get fluid, we are bound to send about 0.5 to 1 milliliter for cytologic analysis. And we're also bound to send 0.5 to 1 milliliter for tumor marker analysis, neither of which are terribly sensitive for the detection of invasive pathology or dysplasia within these lesions. But any sort of clinical trial that may arise that we may think of, that we think that will usurp Sendai criteria, needs to be able to be done within this context, within this current clinical standard. Moreover, data from a colleague of mine, Michelle Anderson at the University of Michigan, has shown that pancreatic cyst fluid contains plenty of inhibitors of routine PCR reactions, making it very difficult to deal with here. And finally, if we're talking about something that could potentially be incorporated into clinical diagnostics, the workflow needs to be streamlined and technically simple. So it's in this context that we turn to the Thunderbolts panel. And so this is, so I'll be presenting pilot data driven by my postdoc, Angelina Landana Joshi, who was fresh out of her Ph.D. thesis just in June. So she joined the lab in July, and she had little in the way of genomics experience, and yet she was able to drive this project. So here the hypothesis is that we can obtain a genetic signature found in about 10 microliters of cyst fluid, corresponding to 10 to 50 nanograms of DNA. And so here we would like to find a genetic signature that can distinguish between benign and advanced pathology in resected SNDI-positive cyst lesions. And so this pilot trial involved looking at 5 cyst fluid samples from patients who eventually underwent surgery. We prepared DNA, extracted it, and performed Thunderbolts targeted amplification, library construction, and sequencing. We confirmed the mutations by digital PCR, and then we compared the genetic signatures to the resulting pathology. So here's the standard data. It looks very similar to what you've seen before. And we see that we see the 5 different samples, but we have very similar data no matter if we put in 50 nanograms or 8 nanograms. We get very uniform coverage and deep coverage at that, going out to almost 200x for almost all the targets. In terms of mutation detection, we got some very interesting data. So in samples 4 and 5, we found benign pathology. And here, not surprisingly, we could not find any mutations. But in the 3 samples in which we found advanced pathology, invasive carcinoma or dysplasia, we find that every single one had either a codon 12 KRAS mutation or a codon 201 GNAS mutation. In addition, we found additional mutations in the sample containing invasive carcinoma. Now, we were able to validate these mutations using Droplet digital PCR. Here we're using TACMAN assays right off the shelf. And here we find in sample 1 with the invasive carcinoma a 26% minor allelic frequency. We find 0% events in the benign sample. And similar to what the others have shown, we see extremely high concordance in allelic frequency estimation with Droplet digital PCR with the sequencing data. Now, what was really interesting to us is that we compared these data to a send-out test that many people in the field used from a laboratory that specializes in detecting KRAS mutations from pancreas cyst fluid. And what we're able to see here is that only one of the 3 samples in which we were able to find KRAS mutations using 2 complementary methods where KRAS mutations were able to be detected. So our future directions, we're designing a pancreas-specific Thunderbolts panel. There are some mutations that we see in cyst lesions in ductal adenocarcinoma that are not represented under the current Thunderbolts panel, and we are working with the company to design this. And once we have this, we have buy-in from our institution to be able to do a clinical trial, comparing the clinical utility of SNDI criteria with Thunderbolts-enabled sequencing, as well as targeted mutation analysis using Droplet digital PCR. All right, so I've shown you data today that Thunderbolts-enabled targeted sequencing can be done with as little as 8 nanograms of input DNA from a fluid that's really difficult to work with, pancreatic cyst fluid. And this corresponds to actually 10 microliters of cyst fluid itself. And this allows us now to begin to think about genetic analysis of extremely small lesions that are being picked up on CT scans and MRI as well. And we've been able to show support for our hypothesis. Here we were able to show that KRAS and GNAS mutations certainly do correlate with the presence of worrisome pathology in cystic lesions. So this work was driven by, again, my first-year postdoc, Angelina Joshi, with help from Stacy Coleman. and our key collaborators from Michigan, but mostly from RainDance, especially Rachel Roll, who's been able to help us with some of the intricacies of the protocols and the funding shown here. So with that, I thank you for your attention. I'll be happy to take any questions. Yeah.
So I have two questions. The first one, how do you explain the lack of sensitivity of the outsourced assay? I mean, your mutations were present at 20, 25%. I mean, they should be able to pick that up. You don't need digital droplet PCR.
That was the exact discussion we had on our phone call. I don't know why. These are the data. I can only do some hand waving to say that the cyst fluid has bona fide PCR inhibitors that may not be relevant in our RainDrop enabled assays.
And the second question I had is, what is it going to take to change the standard of care in your institution?
Yeah. So we need to be able to show. To tell you the truth, the bar is going to be low because the current clinical criteria are just horrible. So we'll see what happens. We're still in very early days.
So if you run 100 patients and you show the perfect correlation between the presence of mutation and the disease, then they're going to change the standard of care.
Well, we'd have to get it CLIA certified and whatnot, but yeah, it's a process that we are purposefully not thinking about at this point. Just want to see if it works.
Getting to the question of the outsourced samples that overrun, there's a difference between what the allele frequency is versus what the absolute lower limit of detection is. One hypothesis might be that while the allele frequencies aren't that low and should be detectable, there could be an issue with just that little amount of cyst fluid, where you're running into an absolute limit of detection issue with whatever technology they use. So, it's not just about allele frequency, it's what is the minimum level and absolute level of detection. So that would be my hypothesis. We've seen that before with other technologies.
Absolutely.
So, in description of the challenges in the diseases, you mentioned the micro metastases. What are the challenges for detecting those? What is the standard of care?
Yeah. So we know we actually had a paper come out last month where we do some circulating tumor cell analysis as well. And we've been able to show that in about 30% of patients with these benign cystic lesions with no clinical diagnosis of cancer, we're finding detectable numbers of circulating pancreas epithelial cells in the bloodstream. Now, whether or not these cells represent early metastasis, we don't know. But this is another application of the RainDrop that we plan to be using, because we can capture these cells and ask the question whether or not they kind of look or smell like cancer cells. By performing very low input genetic analysis from these cells. Yeah. That's right. That's right. All right. Thank you.
Excellent. Thank you. I want to just, again, thank our speakers tonight, Andy Brooks, Tony Godfrey, and Andy Rim again. Please give them a round of applause. This is obviously very exciting data, early days, but as a company, we're continuing to push the frontier and hopefully give you better tools that make your lives easier while giving you opportunities to look at data that hasn't hitherto been possible to look at. And I think certainly in the three cases we heard today, our goal as a company is really to empower the research that you're doing, and hopefully we're able to do that. There were a couple of other people in the room who have RainDrops, who have plans to use them for a variety of different monitoring applications, as well as rare allele and high sensitivity assays, but I see that at least one of them has stepped away from dinner, so I wasn't going to put him on the spot and ask him what the Mayo is going to be doing on a go-forward basis. We appreciate your coming today. We hope you've enjoyed both the conversations, the company at the table, as well as the presentations here. Obviously, we've got a number of RainDance folks at the various tables, and we hope to be able to work with you as you continue to advance all of your research studies. I'm pointed in the back here. We have a couple of small gifts for you. Please take it as a token of our appreciation. Justin in the back is holding a RainDance umbrella, as well as personalized cross pens, which I think you'll find are quite nice. So please take those as a token of our appreciation for this evening and enjoy the rest of your evening. Thank you very much.